So, welcome back, everybody. This afternoon, we are thrilled to host yet another thought provoking session, this time on a topic that truly opens the doors of quantum learning to everyone. We don't need to be physicists or mathematicians to start in quantum machine learning. Our guest for this session is joining us online all the way from Berlin on the occasion of Qiskit Fall Fest 2025 being hosted at RGUKT, Srikakulam. So please join me in warmly welcoming Dr. Frank Zickert, quantum algorithm engineer and trainer. Dr. Frank has been working at the intersection of quantum computing and machine learning for over 5 years, serving as a quantum algorithm engineer and trainer at PIQML since 2020. Through his work, he focused on many quantum concepts, practical and accessible for developers, students, and industry professionals alike. He holds a PhD in information technology from Goethe University, Frankfurt, and a master's in banking and financial support services from the Frankfurt School of Finance and Management. His strong technical and analytical foundation enables him to bridge the gap between classical computing, machine learning, and the quantum frontier. So, Dr. Frank is also a renowned author of the Hands on Quantum Machine Learning with Python series, Volume 1 Get Started, and Volume 2 Combinatorial Optimization, which together forms one of the most practical guides for anyone eager to explore the quantum machine learning without needing to master any theoretical physics first. His mission is clear, guys, to help enthusiasts, developers, and students become quantum machine learning practitioners regardless of their academic background. His approachable teaching style and step by step practical insights have already inspired thousands of learners across the world. So, without any further ado, let's all extend a very warm virtual welcome to Dr. Frank and hand over the session to him as he takes us through today's engaging topic. We don't need to be physicists or mathematicians to start in quantum machine learning. So, sir, the virtual dais is all yours.
Hello, thank you for the warm introduction. Um, I'm starting to share my screen. Just 1 second, please. Great. Can you see it?
Yes, sir, it's visible right now.
Okay. Okay, thanks. So, when you start learning about quantum computing, you will face many claims about the potential of this technology. Um, just 1 second. So, just have a look at what McKinsey, for instance, says. They say the emerging technology of quantum computing could revolutionize the fight against climate change, transforming the economics of decarbonization and becoming a major factor in limiting global warming to the target temperature of 1.5 degrees Celsius. And other sources, such as Forbes, seem to agree the application of quantum technologies could transform the energy industry and lead to cleaner energy with fewer emissions. Both of these sources are completely reputable, and the articles also suggest that they have been thoroughly researched. But they are not selling research results, they are selling hype. Big consulting firms, global magazines, major tech companies, they all repeat the same prophecy. Quantum computing will change everything for the better. But basically, their claims are worthless because they both fantasize about what quantum computing could enable us to do in the future. They're clever. They always use the word could. So technically, they're not making any false claims because without a doubt, new technology could lead us to all sorts of things. But of course, these hypesters know the power of words and that could will be interpreted as will. They do not even explain or prove why quantum computers will solve these problems. Their main argument goes something like this. We know that quantum computers are capable of solving difficult problems. And here's a list of problems that we have no idea of how to solve them. And that's why a quantum computer is the right tool. So if you listen closely, there's no how, just big words and shiny predictions. They thrive on your curiosity. They want you to be excited, not informed. And that's exactly where most beginners fall into the trap, between wonder and confusion. When you start exploring quantum computing, you enter a world of strange truths, a world where the line between fact and fiction is barely discernible. The simple reason for this is because quantum computing is still so poorly understood. But quantum computing will only change the world if people like you, programmers, engineers, data scientists, and students, learn how to use it properly. When we stop treating it like sorcery and start treating it like technology, not through mysticism, but through clarity, practice, and reason. And this is what today's talk should be about. How can we programmers, engineers, data scientists, and students learn quantum computing at all? So, if you really want to learn quantum computing, it's time you turn to more serious sources, like introductory courses. At first, the beautiful explanations of quantum mechanical concepts will cast a spell over you. A qubit can be both 0 and 1 at the same time. And you think, that's beautiful, that's elegant, that all makes sense. Finally, someone explains it understandably. They speak softly, clearly, and sound trustworthy, just like the sirens in Homer's Odyssey. As soon as you go into detail, they reveal their gruesome fates. Suddenly, the superposition is a two-dimensional quantum system that's usually denoted as a quantum state kept psi, such as a qubit, is a complex linear combination of its mutually orthogonal basis state vectors. And the sirens don't lie. They just leave out the important part. They replace understanding with metaphors and then abandon you. They don't say that a qubit isn't really both 0 and 1. It isn't in two states. It is in a particular quantum state that we just can't observe directly. They just leave you with Greek letters, vertical lines, strange symbols, and no explanation of their meaning. They skip right over the part where intuition fails. The sirens thrive on incomplete understanding, on that satisfying illusion that you almost understand. They make you feel smart just long enough until you feel stupid again. And then you start wonder, maybe you do need a degree in physics after all. Maybe you should go bridge between your own world and theirs. You find an impenetrable wall. You find only an alien landscape of symbols and assumptions. You calm down and accept. If you ask why an algorithm works, you learn about interference patterns and unitary. Beautiful, it's rigorous, and it's completely impractical for someone who wants to understand something. The mathematical resources are not more forgiving. They remove the physical metaphors and replace them with symbols. Where the physicist draws a diagram, the mathematician writes a definition. Where the physicist says a qubit interferes with itself, the mathematician says ket psi is a combination of alpha ket 1 and so on. And these are not the extremes. These are the normal teachers you encounter in quantum computing. They insist on rigor, but they exclude intuition. They describe, but they do not translate. You feel like an intruder in a foreign country. You recognize some of the words, but you cannot participate in a conversation. The knowledge is not hidden in the equations, but in the silence between them, the part that no one wants to translate for the eager learner. It took me a long time to realize this. I stopped waiting for the right book or the right course. I stopped trying to understand the universe. Instead, I started to use it. I opened a Jupyter notebook, wrote my first quantum circuit, and executed it. And suddenly, the fog started to clear. That was the turning point for me. Just look at these few lines, and that's it. I press run for the first time, and I wasn't reading about superposition and entanglement, I was creating it. No metaphors anymore, no equation, just a few lines of code. The results weren't dramatic. 2 measured bits, seemingly random at first glance. But they had a meaning. I could see the change in probability distribution when I added a gate, changed the circuit, when I removed a gate, and so on. For the first time, I could observe the abstract behavior of a qubit and didn't just have to imagine it. That was when I realized what I was missing from all the textbooks. Understanding doesn't come from memorizing equations. It comes from interacting with them. When superposition and entanglement were discovered, they didn't have computers to do the math, not even classical computers. But today we don't need to multiply the matrices by hand. We have computers. They do it well and they do it fast. So let them do the work they do best so that we can focus on what we do best. And that means making sense out of things. The more circuits I built, the more concepts began to make sense. Superposition was no longer magic. It became the result of a Hadamard gate. Entanglement was not a philosophical conundrum. It became simply what happened when you connected a C-knot behind the Hadamard gate. Measurement collapse? That was the part where I click run and saw one result trump the others. Physics hadn't changed. What had changed was my relation. Most people approach quantum computing in the traditional way. First, they learn theory, then the equations, before they start code, and finally, maybe or maybe not, they learn the concept. They start with the most difficult part and end with the most intuitive. No wonder most of them give up. But when you reverse this order, something remarkable happens. You start with practice, you start with code and conceptual thinking, then you develop intuition first. The math becomes an explanation rather than an obstacle. So, from my point of view, the correct order is first learn the concept, then use the code before you go to the equations, and finally dive into the theory. So learn what a system does, not why it does it. Use it, explore it, observe when it behaves unexpectedly. Only then you go back and let the theory explain what you have already seen. This simple reversal turned confusion into understanding for me. For me, programming quantum circuits replaced the noise of technical jargon with the clarity of cause and effect. And in doing so, I discovered something else. Quantum computing wasn't as strange as it seemed. It was simply a different system, a system governed by logic, structure, input and output. And you don't have to understand quantum mechanics to use it. You just have to understand how it behaves. This realization became the basis for how I teach and write about quantum computing today. Not as abstract physics, not as mathematical exercise, but as a technology. Quantum computing is something you work with, not something you worship. When I started building things, something unexpected happened. The voices that had previously confused me, the physics, the ghoul, the sirens, not even the hype stuff, they suddenly sounded different. Once I began to understand through practice, I realized that none of them were completely wrong. They were all just incomplete. The physics sorcerer is right about one thing. Without rigor, everything degenerates into buzzwords. His language always sounded like an incantation, unitary operators, decoherence, Hilbert spaces. But when I started programming, I realized why he insists on the precision. A single false assumption can render an entire algorithm meaningless. I am not yet fluent enough to think in this language. I do not understand particles or wave functions. But I have learned to be interested in the truth behind the concept. The obsession with accuracy prevents us from getting lost in ambiguous metaphors. And the ghoul has its own kind of truth. Its symbols should not exclude anyone. They are meant to protect meaning. Every equation is a safeguard against misinterpretation. At first, the equations looked like barriers. Now I see them as contracts, clear, unambiguous statements about what must be true. Once deciphered, they do not obscure understanding, they stabilize it. They force you to question your own beliefs. When it is confused with a goal, used correctly, it is a bridge between curiosity and understanding. They taught me that metaphors are not lies, but scaffolding. And even the hypesters, with their exaggerated headlines and wild promises, served a purpose. They remind me why the topic was important to me in the first place. Quantum computers have great potential. They could revolutionize optimization, simulation, logistics, and research. Their exaggerations are clumsy, but their instincts are right. This technology is important. But ultimately, none of these characters are pure villains. They are specialists, each preserving one aspect of understanding: rigor, precision, intuition, motivation. You need all four of them. The challenge is not to silence them, it's about translating between them, weaving their strength into a learning method that feels human. That's what I've built my teaching approach on. It blurs the rigor of the physicist, the precision of the mathematician, the intuition of the siren, and the motivation of the hypester. But I rearrange them into a path you can actually walk. But just when I thought I had found balance, when I had learned to navigate between math, code, and practice, a new villain appeared on the horizon. Not a sorcerer, not a ghoul, not even a siren, something far more mischievous. The Qiskit squirrel. It didn't come quietly, it was announced with trumpets and fanfare. The squirrel updated Qiskit to 1.0, then to 2.0. Every single tutorial, every blog post, every GitHub notebook, they all stopped working. Dozens of examples I had used to teach myself quantum circuits no longer worked. Import errors, outdated functions, missing parameters. My entire approach seemed to collapse. If the code doesn't run, you can't see what it does. And if you can't see what it does, you can't understand how it works. I found myself back in the complete darkness. The new API is, of course, very well documented in pages of concise technical details that read like internal notes written by software engineers for other software engineers. It almost seems as if you need to be a computer scientist to understand it. But of course, that can't be true, and it isn't. But it teaches us that there is another trait we need to embrace rather than suppress. Practical quantum computing is still in its infancy. It is still in the process of laying its foundations. Every new version, every API change is a symptom of an emerging field. To the learner, however, API I was using and focused on mastering the underlying concepts. Because concepts survive version changes. Understanding outlasts syntax. After the chaos with the squirrel, I understood something simple but crucial. You cannot control how quantum computers develop. You can't control how research papers are written. You can't control when the next version will destroy your code. But what you can control is how you learn. You don't have to learn quantum mechanics. You don't have to get a degree in physics. You don't have to memorize every matrix identity. What you need is a learning framework that adapts as quickly as the field itself. And for me, this framework is simple. You start with a concept, you code, then you go to the equations and learn the theory of all that. Start with a concept. What does the system do? How does it inform and how does information flow? What do superposition and entanglement mean as operations? Then move on to the code. Test it, run it, observe its behavior. Only then you return to the equations, not as obstacles, but as a confirmation of what you already know. This order reverses the traditional order. It does not trivialize theory, but it grounds it. And that's how I developed PIQML. My approach to teaching quantum computing: no more series of lectures or derivations, but a modular, practice-oriented structure that lets you learn by doing. You explore the field yourself, experimentally, iteratively, practically. And that helps for me. And the theory comes naturally when you actually need it. So you don't learn quantum computing by staring at the universe. You learn it by doing, by building one. So when someone asks me today, do I have to be a physicist or a mathematician to learn quantum computing? I answer no. You only have to be a learner who refuses to wait for permission. And quantum computing does not belong to physicists or mathematicians. It belongs to anyone who is willing to think differently. Thank you for your attention. Are there any questions?
Guys, if any one of you are having any questions, you may feel free to ask. Seems like everything is clear from your side, sir.
Okay.
Thank you
Very
so
well.
much for such an insightful session. This is truly insightful, and the way you presented it, it made everything extra special for all of us, especially for the beginners or people who are still exploring the quantum field initially. Your kind of presentation and the way you gave clarity that we don't need to be physicists or experts in mathematics to learn quantum computing, and we learn it by doing. We learn it by doing initially, that we should start doing it. And it is such an insightful and delightful session to, and we are really grateful to have you here, sir. Thanks a lot for all your efforts and all the knowledge you have shared, the insights you have provided, and your valuable time too.
Thank you.